Hello everyone, and welcome to this tutorial on quantum parallelism and its impact on distributed computing. Have you ever wondered how systems like Google's search process of billions of queries so quickly? That's because of parallel and distributed computing, which divides tasks across multiple computers. Now imagine a future where we could process not just billions but trillions of computations simultaneously. That's where quantum parallelism comes in. In this session, we will dive into what quantum parallelism is, how it works, and how it would completely transform distributed systems. By the end of this video, you will understand its potential and the challenges that comes with it. Let's start by understanding quantum parallelism. It's based on two key principles, superposition and entanglement. Here's a simple analogy for superposition. Imagine a flipping coin. While it's spinning in the air, it's not just heads or tails, it's both at the same time. Similarly, a quantum bit or qubit can represent 0 and 1 simultaneously. For example, if you are solving a problem with 4 inputs, say A, B, C, and D, a classical computer processes them one at a time. But with qubit, you can evaluate all 4 inputs at once because of superposition. This massively speeds up computation. Now let's talk about entanglement. Think of it like a pair of connected gloves. If you take one glove and I take the other, the moment you see your glove is right-handed, you instantly know mine is left-handed, no matter how far we are. In quantum terms, this allows qubits in different locations to share information instantaneously, making it perfect for distributed systems. One example of quantum parallelism is action in Grover's algorithm. It can search an unsorted database of 1 million entries in just 1000 steps, a huge improvement over classical methods. Now let's look at why distributed systems today face limitations. Imagine you are at a pizza party with 10 friends and you need to coordinate who will order, who will pay, and who will pick it up. Communication between all of you takes time and effort. This is similarly to communication bottleneck in distributed systems where nodes spend too much time exchanging data. Another issue is fault tolerance. If a person forgets their task, the whole plan might fall apart. Similarly, if a node in a distributed system fails, it takes a lot of resources to ensure the system keeps running smoothly. There's scalability. Adding more friends to your pizza plan makes communication even harder, just like adding more nodes to distributed system can reduce efficiency due to increased synchronization overhead. These challenges create a need for new solutions, and quantum computing might just be the answer. Now let's talk about some exciting application of quantum parallelism in distributed systems. First, quantum cloud computing. Imagine using a quantum server as a part of a cloud network. For instance, let's say we are simulating the weather. A quantum cloud can process multiple atmospheric scenarios simultaneously, providing accurate predictions much faster than classical systems. Second, quantum enhanced blockchain. Blockchain involves validating transactions which require heavy computation. Quantum parallelism could speed this up dramatically, making systems like cryptocurrency more efficient and secure. And third, distributing machine learning. Think about training an AI model with dataset containing millions of images. With quantum computing, we can use quantum kernels to perform computations in parallel, reducing training time significantly. This could be revolutionary for industries like healthcare, where faster AI models could save lives. While quantum parallelism is promising, there are some significant hurdles to overcome. One major challenge is hardware limitation. Imagine trying to run a high-end video game on a 10-year-old computer. It won't work well. Similarly, today's quantum computers are small and fragile, making large-scale applications difficult. Another issue is error rate. Let's say you are drawing on wet paper, it's easy to make a mess. In a quantum computing, qubits are highly sensitive to their environment, which can cause them to lose their quantum state. This is known as decoherence. Finally, there's challenge of integration. Think of combining a modern smartphone with a rotatory phone. Similarly, integrating classical systems with quantum systems require complex engineering to make them work together seamlessly. These challenges means that while the future is bright, it will take time and efforts to fully realize quantum parallelism's potential. To wrap up, let's revisit the key points. Quantum parallelism allows us to process multiple inputs simultaneously using properties like superposition and entanglement. This could revolutionize distributed computing by addressing current issues like communication bottlenecks, fault tolerance, and scalability. However, challenges like hardware limitation and high error rates means that practical implementation is still a long-term goal. Looking ahead, as quantum computing technology evolves, we will see it integrated into distributed systems, unlocking possibilities we can only imagine.